So if somebody can remind me, did we go over Chebyshev's theorem and the empirical rule last class? I believe that's where we left off. You guess so? That you recall. Okay, so if you recall, just quickly on Chebyshev's, you use this formula. Basically, it gives you an approximation of where the data lies with regards to how many standard deviations it's away from the mean. And the empirical rule is making the assumption that one standard deviation above and below the mean occupies 68%. Two standard deviations above and below the mean occupy 95%. And that 99.7% of the data lies within 3 standard deviations of the mean. And remember, both of these assume that you have a standard normal curve, or the bell curve that looks like this. Okay. Are there any questions about that? Remember, these two rules are used when you don't have the complete data. In reality, you probably will have the complete data. But you can use the empirical rule and Chebyshev's just in case you are missing some information. Any questions about that? Amir, did you have any questions since you think we did not cover this? No, it's clear to you? Okay, good. All right. So we talked a little bit about this. The geometric mean and the standard deviation of group data. So we have the arithmetic mean, which is basically the sum of all the values over the number of observations that we have. And this example, we determine the arithmetic mean of a of a vehicle selling price given in the frequency table below. Now, this is grouped because what they're doing is they are grouping the cost with the category of selling price. So we have, 15,000 to 18,000, the frequency, the midpoint. And we have the categories from 15 up to 18, up to 33, up to 36. So you can take continuous data, this is what's important about this, and group it. Okay? The groups have to make logical sense. It's not arbitrary. You have to base it on some kind of important information. So just remember that. You cannot just group it just because you want to group in some way. And if you look at this grouping, you see that it's 3 categories, 15, 16, 18, four variables within this grouping, okay? If you're going to group data, it has to be consistent through all your data. So all these have 4 items within each group. And figuring out the standard deviation is the same way you figure out the standard deviation, but it's just for these groups. So you think of them as 1, 2, 3, 4, 5, 6, 7. And we find the mean of each of the groups and figure out the standard deviation. Exactly the same as a regular standard deviation, except for this is grouped data. So you can take grouping data, and your dependent variable is continuous. You put the continuous variable in whatever group it belongs to and can still figure out what the standard deviation is. Are there any questions about that? No questions? Okay, great. All right. Okay. You can pronounce this as z-scores. I like to pronounce it as z-scores since this is Canada, and I know I grew up here and followed the British way of pronouncing the letters. So for me, it's a z-score. So simply put, the z-score is the number of standard deviations from the mean a data point is. But more technically, it's a measure of how many standard deviations below or above the population mean a raw score is. So can somebody tell me why that's important to know? Why would you want to know this? Everybody having their afternoon nap? Okay. The z-score becomes extremely important. And again, I'll emphasize, this is based on a standard normal curve. But what a z-score actually does is standardize the data. So you've heard of maybe perhaps when you were in school, you had a test, the teacher, oh, I'm going to bell curve it. That's what you do when you have z-scores. You standardize the data so it approximates a bell curve as much as possible. So the mean is 0 and a standard deviation is always 1. Okay? Which makes it a lot easier to look at a data point that you're examining to see whether it's statistically significant or not. So the z-score is also known as a standard score, and it can be placed on a normal distribution. And the z-scores usually range from -3 to +3. Okay? It's very, very rare that you will ever come across a standard deviation that is more than 3 or greater than 3. So in order to use the z-score, you need to know the mean, mu, and also the population standard deviation, sigma. And z-scores are a way to compare results from a test to a normal population. And the results from the tests or the surveys have thousands of possible results in units. However, those results can often seem meaningless. For example, knowing that someone's weight is 150 pounds might be good information, but if you want to compare it to the average person's weight, looking at a vast table of data can be overwhelming, especially if some weights are recorded in kilograms. A z-score can tell you where that person's weight is compared to the average population's mean. And if you recall, I previously mentioned that when you obtain a z-score for whatever it is, a test mark, an observation that you're doing, and it lies within one standard deviation, which means it goes from -1 to +1 standard deviations, usually that number, which is usually a mean, is not going to be statistically different than the population mean, okay? And that's what you're trying to do, whether there's statistical differences or there's not. And usually when a number is greater than or less than 2 standard deviations from the mean, most of the time, 99%, that is going to be statistically different. And therefore, you have a statistically different result that you can talk about. And this is something that you can do for your project. When you get the data, you can standardize it, find the z-scores, see where the mean is for the populations that you have. And I mean, you have to run other tests, but usually if it's greater than or less than 2 standard deviations from the mean, it may come out statistically significant. Is there a question about z-scores? No questions. Okay, so I'm going to play the video of that. Okay. Okay.
I'm going to show you an example of calculating z-scores. This is actually a redo of a video. The formula for z-score is observation minus the mean divided by standard deviation. The typical symbols are z is equal to x minus the mean divided by the standard deviation. Those would be the typical symbols. In my example, let's assume the mean is equal to 15, the observation is equal to 10, and the standard deviation is equal to 5. I just made up those numbers. I'm going to plug the values into this equation. So I have 10 minus 15 divided by 5. This equals to negative 5 divided by 5, which equals negative 1.
And I'm just going to remind everybody, z-scores can be negative. So don't be concerned if you get a negative result when you compute a z-score.
Now I can ask, what is the probability an observation is more than 10? And also I can ask, what is the probability an observation is less than 10? The first thing I do is I draw a bell curve. I draw the mean right in the middle, which was 15. I put in the location of the observation, which was 10. I would recommend putting the z-score of -1 and 0 in as well. By the way, the z-score at the mean is always 0. I will determine the area between 10 and 15, and I'll add that to the area above 15. So this blue area is equal to 0.3400. I determine that by looking up -1 in a standard normal table. The area above 15 is 0.500 because it's half the bell curve. And these two areas added together equals 0.8400.
So just so you're aware, I mean, we are going to start the next chapter, which is probability. So if somebody asks, oh, what is the probability of this score occurring? So we know, even in a normal bell curve, anything between -1 and +1 standard deviations is 68% of the data. For 2, it's 95%, and for 3 standard deviations, it's 99.97. Okay, so let me just say this 50% is from the mean and goes all the way to the end, and that's 50% of the data. This is a bell curve, so it's just a mirror of the other. So anything on one side of the mean is going to be 50%. We know that one standard deviation above and below is 68%. You just divide it by 2, that's 34%. So we're adding 34% plus 50%, 84%.
Or 84%. The whole area above 10, the observation at 10, this is gray area here, and it equals to 0.8400, or about 84%. The whole area under the curve, this gray area right here, is equal to 1, or 100%. The area that we just had was this dark gray area of 0.8400. So this light area, which we want to determine now, is 1 minus 0.8400, which is 0.16, or 16%. So 0.166 is the probability of an observation being less than 10. So an observation being more than 10 is 0.8400, that area there. An observation less than 10 is that area there, which is about 16%.
Okay, so remember, this is a curve that goes from minus infinity to plus infinity, but we're only concerned with the standard deviation. So we know that the area under the curve is 100% or 1. We figured out the 84%. So what's left is 16%. So it's usually 1 minus the 0.84, which is 16, which is 0.16 or 16%. So get confused because you are using minuses when you're doing Z-scores. Okay, we haven't really talked about it, but there are tables. It's in the formula sheets, and you may get a question about, the area under the curve is, 2.6. You figure it out. It will tell you. You don't have to figure that out. You just have to look it up in the table. It will tell you how much area that takes up, 91%, 90%, 90.6%. So I just want you to be aware of that it seems complicated, but it's rather easy because it's all based on number 1. So you can't go over 1.
So let me summarize for you and walk through the steps that I did. Step 1 is draw a bell curve. This is very useful. So I'll draw that in there. Step 2, put in the mean value. In our case, it was 15 right in the middle. Step 3, put in the observation, which in our case was 10. Calculate the z-scores. It was -1 and 0. Step 5, fill in values and calculate. So the values were 0.1600 and 0.8400. This has just been a quick little example of how to calculate z-scores.
Okay. So any questions about Z-scores or Z-scores, whatever way you want to pronounce it? No questions? All right. Okay, John, good. All right, so the formula, Z equals X minus mu divided by sigma. So for example, let's say you have a test score of 190. The test has a mean or mu of 150 and a standard deviation of 25. And this is very important. Remember, always assume a normal distribution. You will be told when it is not a normal distribution. So the Z-score will be Z equals X minus mu divided by sigma. In this case, 190 minus 150 divided by 25 equals 1.6. And hopefully, I hope everybody in their previous math course learned how to manipulate numbers in case, in this case, say you didn't know Z, but you knew mu. You still can figure it out, okay? Or you didn't know the mean, but you had all the other information. So you can just substitute that way. And the Z-score tells you how many standard deviations from the mean your score is. In this example, your score is 1.6 standard deviations above the mean. Sometimes you may also see the Z-score formula shown to the left here. Is exactly the same as Z equals X minus mu divided by sigma, except that X bar, the sample mean, is used instead of mu, the population mean. And S, the sample standard deviation, is used instead of sigma, the population standard deviation. However, the steps for solving it are exactly the same. Now, what you usually do when you use Z-scores and you have a sample population, what you're doing is you're saying, well, your hypothesis is saying, is this the same as the population or is it not the same as the population. So when you're figuring the z-scores, as it says, you can use the exact same formula, except you're substituting the sample mean and the sample standard deviation. Any questions about that? Everybody's got the z-score. Okay. This is another measure, the standard error of the mean. So when you have multiple samples and want to describe the standard deviation of those sample means, it's referred to as the standard error. You would use a z-score formula, z equals x minus mu divided by sigma divided by the square root of n. So this z-score tells you how many standard errors there are between sample mean and the population mean. So an example. In general, the mean height of women is 65 inches. Sorry, it's American. With a standard deviation of 3.5 inches. And what is the probability of finding a random sample of 50 women with a mean height of 70 inches, assuming the heights are normally distributed? So don't always make that assumption, but the assumption should be made for you and tell you that every variable that you're looking at is normally distributed. So you know it's a bell curve. So we have the standard formula z equals x minus mu divided by sigma divided by the square root of n. Substituting the numbers, 70 minus 65 divided by 3.5 divided by the square root of 50 equals 5 divided by 0.495 equals 10.1. So what's important? The key is that you're dealing with a sample distribution of means. So we know we have to include the standard error in the formula. You also know that 99% of values fall within 3 standard deviations from the mean in a normal probability. That's the empirical rule. Therefore, there's less than 1% probability that any sample of women will have a mean height of 70 inches. Okay. Because this z-score is extremely, extremely large, which means there might be somebody with a mean height of 70 inches. What's the probability? It's very, very tiny, so it's less than 1%. Does everybody understand that example? Are there any questions about that? Okay, so I'm going to show the video on z-scores. A little slow here.
In this tutorial, I'm going to show you.
Okay. Okay, that's weird. Oh, that's very weird. It looks like it's the same video. So my error.
In this tutorial, I'm going to show you an example of calculating the z-scores. This is actually
Let me, sorry, I'm just seeing if it's the
a
same.
redo of a video. The
Okay.
formula for z.
Oh, same person, different topic.
Z-score is observation minus the mean divided by standard deviation. The typical symbols are Z is equal to X minus the mean divided by the standard deviation. Those would be the typical symbols. In my example, let's assume the mean is equal to 15. The observation is equal to 10.
Oh, sorry. It is the same one. I apologize. Okay. Sorry about that. Oh, that's weird. Okay. All right. So you can use the Z table and the normal distribution graph. So if you have never used the Z table, it will be at the back of the text, or you can look at the formula sheets that are on the course website. So you can use the Z table and the normal distribution graph to give you a visual about how a Z score of 2 means higher than average. Let's say you have a person's weight, 240 pounds, and you know that their Z score is 2.0. So you know that 2 is above average because of the high placement on the normal distribution curve. They're 2 standard deviations above the mean, but you want to know exactly how much above average is this weight. So the Z score in the center of the curve is always 0 in a normal distribution. The Z score in the center of the curve is 0. The Z scores to the right of the mean are positive, and the Z scores to the left of the mean are negative. If you look up the score in the Z table, you can tell what percentage of the population is above or below your score. The table shows a Z score of 2.0, showing 0.9772, which converts to 97.72%. If you look at the same score 2.0 of the normal distribution curve, you'll see it corresponds with 97.72%. So, what percent of the population weighs equal to 240 or above? Can someone tell me? Remember what the 97.72% represents. What do you have to do here? Everybody asleep? Subtract 97.72 from 100. What do you get? What's the number you get? Or 1 minus 0.9772. Okay, 2.28. So what does that mean? It's 2.28, John. Can someone tell me? Now you've got a number. So remember what the question is. A person who weighs 240 pounds. What percentage of the population are they? They're above average, but what's the number? You have the numbers in front of you. You figured it out. Exactly 2.28% or 0.28. All right. So, as I mentioned to some of you in your homework, you're given the numbers. You're producing a graph. In this case, we have a Z score. We know what the Z score is. We know that 97.72% of the population is lower than this 240 pounds. Remember, you're dealing with 100%. So if you take 100% minus 97.72 or 1 minus 0.9772, you get 0.228 or 2.28. Okay. So we can say the person who weighs 240 pounds, one, they're two or above standard deviations above the mean. Okay. They represent only 2.28% of the normal population. We can't say they're obese because, well, unless somebody out there knows, what is the average weight of somebody who obese. But we can say they are not within the one standard deviation. Therefore, they are overweight. All right. So does everybody understand how I came to those conclusions? I'm not making anything up. I'm taking the data that's been given, but when I find out the information from the Z-score, I can say, look this only represents 2.28% of the population. That means that 97.72% are less than this weight. Okay? Any questions about, interpreting what kind of results you get and how you can make them into statements about the data? If you practice this, it will come to you and you'll be, as I said at the beginning, I keep saying it, look at the data from a statistical perspective. All right. If there's no questions, I'll just go on. Okay. So recognizing, and I know there's a lot of info on here, sorry about that. This is about ethics and reporting results. And we talked a little bit about research ethics and recognizing that collecting data for a statistical inquiry may impose a burden on respondents, that it may be viewed as some of invasion of privacy, and that often involves legitimate confidentiality considerations. And we went over this a bit. And people doing this, whatever you want to call them, research, scientists, data analysts, you collect only the data needed for the purpose of the inquiry. You inform each potential respondent about the general nature. You establish their intentions were pertinent to protect the confidentiality of information collected from respondents. You try to ensure that these intentions realistically reflect their ability to do so. Ensure that the means are adequate to protect confidentiality, which is probably the most important. And you ensure that whenever data are transferred to other persons or organizations, this transfer conforms with the established confidentiality pledges and require written assurance from the recipients of the data. Has anybody in the class participated in a survey before? Okay, what kind of questions did they ask you? Can you remember? Nobody can remember any of the questions? Eight, yeah, but did they have anything about confidentiality or releasing the information? That's really, really important, especially if you're going to collect your own data for your case study. So Brenda, can you remember what one of the questions was? Is that a question, Stat Canada? Oh, related with mental health. Okay. And what can you remember sort of what they said about that? Like it's protected, the information will be protected and not released anywhere. Can you recall, Brenda? Yeah, okay. So that's basically, so has anybody done any surveys? I know that some students in marketing try to get other students from the college and participate in their surveys. Has anybody in this class done any of those surveys? Usually you get a payoff of food, like, I don't know, cookies or, you know, Oreo cakes, something, whatever. So nobody's participated or you don't want to participate. Okay, what is that survey? What's that survey, Brenda? No, but what is the survey covering? What is it? What are you giving them? What information are you providing them? Your experience with GBC, and it's anonymous, correct? Okay, right. That's important. Once it's anonymous, let's put it this way: somebody can find out who you are, who did this survey. It's online. Is it online? Okay, so there is a way for GBC to find out who you are. It's just not worth their while to do, but just be wary of that because if you have the right equipment, you can trace anybody's IP and the IP can be linked to a location and the location can be linked to a student number. So just remember that. But because it's anonymous, what they usually do is when they collect the surveys, they just take out that information. So everybody who does a survey, they're just going to assign a number. You're number one or number two, whatever it is, up to whatever, how many respondents they get. So let me see if we've seen this video before.
I love reading a study that makes me believe wholeheartedly that this variable is in fact going to explain a relationship that is intriguing and then it doesn't work. It doesn't turn out that way. And I think as scientists, some of the discoveries that we make that are most interesting are the ones that are non-conformational, where we get results that we didn't expect.
Nor should we add variables through a fishing expedition to see if we can find something that quote unquote worked, or otherwise massage, analyze data, and then after the fact try to come up with a theory that tells a good story that we can then wrap around the data.
You really need to report results accurately, whatever they are.
I would say a study works when it's well designed and gives valid answers to important questions. The answers can be no, and that study will still have worked.
We owe each other to share because other scientists would believe the same thing to be true.
I just want to stop there because I want to mention to you, if you decide you're going to collect your own data, don't be concerned if you're not getting the responses you think you might get. As one of the speakers said, it's important to have all the data, whether it follows your hypothesis or it doesn't, because that's also an interesting aspect of doing the research. Okay?
As they start their research, and if we leave that out of our report, we're causing other people to go down that same road without really thinking along with us, why did this happen?
Okay, so are we obligated morally, ethically, as a matter of scientific principle, to share data with others? Some institutions, such as the American Psychological Association, have that as an explicit policy. That for a period of time, you should make your data available for someone else who wants to conduct a reanalysis to perhaps use the data in different ways, or to verify that what was reported was in fact what the data would show.
Should we always report the source of instruments that we use, particularly if they're developed by others? Absolutely. We do occasionally see in articles that are submitted to journals instruments that are included and used for research without citation, and it's important for reviewers to catch that and correct that if it.
I'm going to ask a question. Has anybody seen the movie Dark Water? No? Okay. It's kind of statistically rated. Have people heard of the company called Dow Chemical or DuPont? It's a giant company, a pharmaceutical company in the United States. And what they were doing was they had set up plants in a small town in West Virginia. And what happened was they were throwing all the chemicals that they made. One of the things they make is rubber, like for tires. And they were throwing all the chemicals that they don't use in the tires, but are needed to make the tires, into the water system of the small town. And what was happening was that residents of the town were having strange things happen to them, including dying, and there was genetic mutations. And where are all these reports? They were in-house. They never published them. So nobody, until this started happening, knew what was going on with these chemicals. Like animals were dying, people were dying. So that's why it's really important, but they're not monitored. That's unfortunate. But that's why when you do some research, and whatever kind of results you get, you should always share them with others.
Happens to be missing in an article that an author has submitted because the people who did the original work or who collected the original data for secondary analysis do need to be given credit for their original work. That's very important. And now it is, I think, a requirement that we do be upfront and forthcoming about where the sponsorship for our research came from. Because obviously, if it in any way could influence the findings, the collection of the data or interpretation of the results, we need to acknowledge that we were funded by people with an interest in certain outcomes. And that just helps us to be clean about the findings and the interpretation of our research in the larger community.
There really is a need for transparency in reporting the processes by which the data have come to be the data we have.
I also think it's important to be transparent to help people understand good methodology. So future researchers, if they're going to study some of the similar phenomena, will also not only understand what you did, but be able to either replicate what you did in order to replicate the study, but even for future studies, it may extend it. So transparency is really important for multiple reasons, and some of it is not just to ensure that it's well done or ethically done, but also that it helps us in terms of our future research.
You cannot anticipate what value there is in full transparency, but the value far exceeds, I think, the perceived threat on the part of authors that I might reveal something that's going to cause my paper to be rejected. I think actually people will appreciate the fastidiousness and the care.
Okay, I'm just gonna stop it there. I'm gonna just do a little poll here. I just want to ask people a question. Oops. Okay, so I put up a poll. If you can answer the questions. Well, it looks like the same three people that didn't answer the last poll from the last class. That's interesting. Okay, well, there's 13 total respondents, and 10 said they're familiar with APA, and 3 said no response. So I don't know whether you know what APA is or you don't know what APA is. Okay, when you do your case study, you're going to use the APA format for the report that you're going to give to me. So as long as most people understand that, that's great. So we've gone through this a little bit before. You can look at it for statistics. And that basically is the end of chapter 3. And as I mentioned, the Chapter 3 test will be available as of 5 p.m. today, and you have up until 5 p.m. on Monday to do the test. So is there any questions about Chapter 3? Okay, so just remember, you know, I prefer you to do it now. I mean, if there's some kind of burning question that you have, you know, send it to me if you haven't started the test. Okay, so now we're going to start Chapter 4. Okay, Brenda, what's your question about the assignment? Okay, so Brenda, what's your question regarding the assignment? Oh, okay. Why didn't you ask me that in the office hours this week? Okay, let me get the book here. Let me look at 370. Okay. So what does the empirical rule say? Oh, you can't find the question. What? Okay. 370 is on page 116. I sent this note twice already. Do you not have access to the e-text?
Hi, Pastor. Yes, I do have access with the e-text. It's just I can't find which questions we need to answer.
Okay, I sent it out. Okay, you have to do 3-68 to
Oh yeah, I got that one because I sent you an email, right? And then
68,
you sent it to
69.
me. I just didn't find it on Wednesday. That's why I wasn't able to ask you in advance
Okay,
on
so
your office end.
368 to 370. And then there was the case study 3.2 on page 120. Okay, so you know what? You can send it to me over the weekend. Okay, anybody else that did not get the questions for the Chapter 3 homework? Look at the email. It's 368 to 370 plus the case study on case study 3.2 National Call Center. And it's question 9, but basically you have to do all the charts and the graphs for question 9 because it says write a report. Okay. Wellington, you asked on the test, will you have calculations? Yeah. So, I mean, you have the textbook, you have the formula sheets, and Samar, the Chapter 3 homework was for today at 5 p.m. Anybody else? You want to send it again? Send it again. Right. Okay. All right, that's kind of weird. Yeah, hello. Okay, so chapter 4 is about probability. Can someone tell me what they think probability is? No one has an idea about probability. Yeah, is a chance an event's going to happen. It's more likely to happen? No, not necessarily. Probability just tells you, is there a chance, as Wellington has said. There's a chance something can happen. There's a chance something can't happen. Can you think of something in everyday life? It's not possibility, it's probability. No, it's not more likely to happen, because what if there's, okay, think about in everyday life, there's a group of people who always use probability every single day. Who are these people? Actually, my son is one of these people. So who would these people be? Can you think? What is it that every day you get something that's related to probability? And they tell you this too. Exactly. My son is a forecaster. He's a meteorologist. Because the weather forecast, whether you watch the TV, the radio, your computer, it'll say, oh, and there's a 10% chance it's going to rain today. I know that's not important for most of you, but how do they come up with that 10%? Can you think of how that happens? No one? They just look out the window and say, it might rain today. How does data lie, Amir? Data doesn't lie. Data is data. Instruments? Does everybody know that there are satellites, weather satellites, that are traveling around the planet? Yeah, they analyze the data from these satellites. Okay, so there are a number of different satellites. There's a Canadian one, there's a British one, there's an American one. Those are the three I know of because he's told me. And how many variables, not for each country because the satellites are going around the planet, and some countries, because satellites are expensive, will get forecasts from other countries. But how many variables do you think there are being used to predict a weather forecast? A lot? What's the number, Wellington? Give me a number. Somebody give me more than 200? No, unfortunately, no. If you had 200, the forecast would be way better than they are now. There's approximately, and because there are different, they're referred to as weather models. You have a British model, a Canadian model, an American model. They use different variables. They don't all use the same variables. So there's approximately between 30 and 50 variables used to predict the weather. Now, this is what my son has told me. Yeah, it's not more than 200, 30 or 50, which is still a lot of variables. What my son has informed me is if you require a forecast for 24 hours, the probability of them getting the forecast correct is greater than 95%. when you look at the weather, if you go to any weather websites or you hear the weather, it'll say, oh, here's a long range forecast for 7 days. And so say there's one today and they'll say, yeah, next Friday is going to be cool with the chance of rain and sunny in the afternoon, you know, stuff like this. That accuracy is probably less than 10%, because you don't know what's going to happen, you know, in the air, in the stratosphere, and a storm may form and it will change the whole forecast. So that's what I'm trying to get at is that's what probability is. You're using the data to predict something that will happen in the future. Okay? And it's never 100% correct. Okay? Sometimes you can get up more than 95, which is usually the expected value. But if you get a probability of less than 95%, that's not usually a good probability. Okay? So that's what we're going to talk about. Has anybody, I don't know if you're old enough, has anybody gone to a casino? Yes. Amir, did you win or did you lose? Amir? You lost, Wellington? Was it a lot of money you lost? Well, what is luck? Tell me what luck is. Amir, what's luck? You wanted to see how it was. That's not luck, Amir. That's probability. Okay? I'm going to say something you probably won't like. There's no such thing as luck. Okay? You know, from a statistical perspective, there is no luck. I don't know, based on chances on how the dice, for example, will roll a 1. Well, that would be 1 die, not dice. But that's, now I don't know whether you've ever seen, there's a movie, and I can't remember the name of the movie, but there were students who, I can't remember whether they were at MIT or they were at Harvard, and they actually came up with a system of playing 21 with the cards, if people are not familiar with that. And the system was they were counting cards. Do you know that for sure, Arbor? 99% chance to lose? Where'd you get that 99% from? Blackjack, not jacket. Blackjack. So these students were counting cards. And usually in a blackjack game, they use full decks with no jokers. They were counting the cards. They got so good at doing this that they were banned from all the casinos in Las Vegas. But they wanted to make a point that you can win because they were using probability. And that was the whole point of my little story. Okay? And not encouraging you to go gamble. However, if somebody becomes, you know, I guess they were obsessed. Oh, is he won, Wellington? No, Amir, the house doesn't always win. Okay. No, the house doesn't always win, you know, unless it's rigged. So you can use probability. I mean, that's the most common thing that people, oh yeah, like betting on, well, I mean, silly, because you might as well go throw your money somewhere and hope that it will double for no particular reason going gambling, because most people don't want to spend the time figuring out probabilities, because that's not fun. It's more fun to be, you know, entertained and lose your money that way. Anyway, So if none of you can remember, if some of you can't remember, probability is about the chances of something occurring, whether it's the rain, whether you roll a 7, you know, whether your team wins the game and you had a bet on the team, or the probability you're going to get an A in this class. What's the probability of getting an A in this class? No sense anything. 50-50. Okay, John. Is that based on just like, yeah, it might happen, it might not happen? Well, if you study and you do practice questions, will not the probability increase? Yes, yeah, exactly. Exactly. If you come to the class, and this is any class, you come to class, you don't come to lectures, you don't study the text, then you probably say, well, and depending on, what kind of evaluations are being used, and let's say all the evaluations were just multiple choice, then what's your chances of passing? Anybody? No, you know what? The chances are 50% because it's multiple choice, so it's just like I can guess correctly. Right? So that it's a 50-50. It's probably going to be lower than that because you may not even understand what the question's asking you. That's for sure. Anyway, so let's start this about probability. It's also a long chapter, so we're probably going to have 2 to 3 sessions, probably 3 sessions. No, you know what? There's no directive on how to make questions. Multiple choice don't have to be hard. Multiple choice can be extremely easy because if you make some of them easy and some of them hard, then the students may not, go, oh, he only makes hard questions or she only makes easy questions. You have to mix it up. Okay? All right. So, probability, experiment, outcome, event. So, probability, a value between 0 and 1, inclusive, describing the relative possibility, which is the chance or likelihood an event will occur. An experiment is a controlled study in which the researcher attempts to understand cause and effect relationships. The study is controlled in the sense that the researcher controls how subjects are assigned to groups and which treatments each group receive. In the analysis phase, the researcher compares group scores on some dependent variable, and based on the analysis, the researcher draws a conclusion about whether the treatment independent variable had a causal effect on the dependent variable. So you're looking at a relationship between some independent variable, something that doesn't vary in the experiment, and the dependent variable, which does vary in the experiment. Okay, so I'm going to get and see if we have the video for this. This is also a very important concept that you should become basically very familiar with, because in business, as I described earlier in some earlier classes, if some of you become financial consultants or financial advisors, somebody's going to come to you and, buying or investing, let's say in like mutual funds or stocks or bonds. It's your job as the advisor, the consultant, to figure out what is the probability that, this investment is going to end up with positive results, or this investment is going to end up with negative results. You want to tell your client not to go for this, even though they may have heard of something. Oh, somebody, I don't recall, I don't know if any of you remember, it was probably, maybe 5 to 10 years ago, some company said they had discovered gold, and I can't remember where it was. It was some island in the South Pacific. I don't know whether it was Indonesia or the Philippines, but they went, oh yeah, we found gold, and then they got all these investors, and what turned out was that's all the gold there was. There wasn't any more. So all the investors lost their money because they thought, oh, this is going to be a get rich quick scheme. And that's what people have to be wary of, that in reality, what you're doing is you're evaluating the data and then you're giving the information or advice to the person that wants to invest. Okay, so let's, get to the video.
Let's learn about probability. To help us learn about probability, let's start by taking a look at chances. Let's say that we take a coin and we flip it. What are the chances of us getting heads? What are the chances of us getting tails instead? How do we figure that out? Or what about randomly drawing out a specific card from a deck of cards? Say, drawing out the ace of spades from a deck of cards. What are the chances of that happening? Is there a way to figure out that chance? In math, when we talk about the chance of an event occurring, what we're really talking about is probability. So let's take a look at the definition of probability. The probability of an event is a number from 0 to 1 that describes the likelihood that that event will occur. So to help us understand probability better, let's take a look at this number line that ranges from 0 to 1. So probability is actually a number from 0 to 1 that describes the likelihood or the chance that a specific event will occur. Now, if we get a probability that's closer to 0, then that probability is less likely. So the chances of that event occurring are less likely. On the other hand, if we
I want to stop because I want you to pay attention to the words that she's using, because these are statistical terms. And usually, when you go into the business world, they're going to use terms like this. So get used to understanding the terms. If it's going towards 0, it's less likely to happen. If it's going towards 1, it's more likely to happen. Okay?
have a probability that's closer to 1, that event is more likely to happen or has a better chance of happening. Now, we can also show probability as a percent. If we do that, then our values would range from 0% to 100%. So let's say that you're watching a weather forecast and you hear that tomorrow there's a 90% chance that it will rain. Well, that 90% would be up here, closer to the 100% mark. So we know that the likelihood or the chances or the probability of it raining tomorrow is pretty good. Now, what about our other examples? Flipping that coin and getting heads. Well, when we flip a coin, we can either get heads or tails, since there's only 2 sides to a coin. So when we flip a coin, we have a 1 out of 2 chance to get heads, or 0.5, or a 50% chance. So since the coin only has 2 sides, we have a 0.5 or a 50% chance to get heads and a 50% chance to get tails. Now, what about drawing the ace of spades out of a deck of cards? Well, a deck has 52 cards, and there's only 1 ace of spades per deck. So that means we have a 1 out of 52 chance to pull an ace of spades randomly out of a deck. That's not very likely. That would be down closer here to that 0% mark. So that has a less likelihood of happening. Now let's take a look back at flipping that coin. We said that if we flipped a coin, the probability of getting heads was 0.5 or 50%. So that would mean if we flip a coin 10 times, we should get heads half the time, or 5 out of those 10 flips. But that doesn't always happen, does it? If we flip a coin 10 times, we may get heads 3 times, or maybe 8 out of those 10 times. Why do our results not match the probability that we had? Well, that's because we're actually dealing with different types of probabilities. So let's take a look. One of these types that we've been looking at so far is called theoretical probability. With theoretical probability, we're actually looking at the probability of what would occur in theory.
Okay, so theoretical, if anybody has gone ahead, is the same as classical. Okay, that's like her example of, flipping a coin. In theory, because there's only 2 resolutions, either it's heads or it's tails, so in theory, it would be 50%. All right, so theoretical and classical are the same.
So in theory, we should get heads half the time when we flip a coin. So if we flip a coin 10 times, we should get heads half the time. But we know that that's not always true. If we actually go out and perform that experiment, we may not get heads half the time every time that we perform that experiment. In that case, we're actually dealing with experimental probability. Experimental probability is based on the actual results from an experiment. So if we actually go and flip a coin 10 times, we may only find that we get heads 2 or 3 times, or 8 or 9 times. So the theoretical probability of an event occurring doesn't always match the experimental probability of that event occurring. To find the theoretical probability, we can take the number of favorable outcomes over the number of total outcomes. To find the experimental probability of an event occurring, we take the number of favorable outcomes that we observe from our experiment, and divide that by the total number of trials. So now we know about these 2 different types of probability. Remember, the probability of an event occurring is a number that ranges from 0 to 1 that describes the likelihood or the chance that an event will occur.
Okay, any questions about that? Pretty straightforward. Okay, so if you break it down, it is rather easy, in finding this information. So that's an experiment. Let me try to make this a little bigger. Okay, an outcome of an experiment is any possible result of the experiment. So if you throw 1 die, what is the possible outcome? Just 1 die, not 2 dice. What are the outcomes? Right, Wellington, 1 to 6, exactly, because you know what the minimum number is, you know what the maximum number is. All right, so that's your boundary, 1 to 6. It can only be from 1 to 6. All right, let me, sorry, I'm going to check on the video for outcome. Sorry, I'm just getting the video up. I think it's the same female there.
What is an
Yeah.
outcome? To figure out what an outcome is, let's start by looking at an example. Let's say we take a 6-sided die and we roll it. What are the different possibilities that we could roll? Well, if we roll a 6-sided die, we could roll a 1, we could roll a 2, a 3, a 4, a 5, or a 6. So if we roll a 6-sided, we could roll any one of these 6 numbers. Each of these is a possible result. Each of these possible results is called an outcome. So say, for instance, that we rolled this 6-sided die and we rolled a 2. That 2 is our result. It's our outcome. So now that we've seen an example, let's look at that definition. An outcome is one possible result we can have from an experiment. So if you have an experiment, like drawing a card from a deck of playing cards, or rolling a 6-sided die, an experiment like that, the possible results that you can have are your possible outcomes. So let's take another example. Let's look at something a little more complicated. Instead of rolling one 6-sided die, let's roll 2 6-sided dice. So now, instead of rolling 1, we'll roll 2 dice. Now here, let's say we roll a 4 and a 6. So we roll a 4 and a 6. This is a possible result we can have from this experiment. It's a possible outcome. Now this experiment is a little bit more complex than our original one. That means we're going to have a few more possible outcomes. So as your experiments to get more and more complex, adding more and more dice, or something like that, that means you'll get more and more possible results, or more and more outcomes. So remember, an outcome is just one possible result from an experiment.
Okay. So she didn't go into talking about what's the probability, but you can imagine from one pair of dice, or sorry, one die to a pair of dice is going to be a lot more. Okay. And the third aspect of probability is an event, which can be one or more incomes. Events can be independent. That means each event is not affected by the other events. Or dependent, which is also called conditional, where an event is affected by other events. This is termed as mutually exclusive. Events can't happen at the same time. So let me find the video for that. And if anybody has any questions, please ask.
The probability of simple events is finding the probability of a single event occurring. When finding the probability of an event occurring, we will use the formula number of favorable outcomes over the number of total outcomes. After calculating this probability, your answer will need to be in simplest form. Let's look at an example of simple events. Sam owns a large fish store with many colors of fish. He keeps all the fish in a large aquarium. In his main aquarium, he has 5 red fish, 6 blue fish, 14 white fish, and 5 green fish. A customer comes into the store and wants to buy a blue fish to take home. What is the probability that Sam will reach in and scoop out a blue fish on his first scoop?
Okay. Can someone, I don't want you to guess, what would it be? Wellington, you say it's 1 in 6? Anybody else? 6 out of 30. And okay, it's 6 out of 30, which you can reduce it to what? 1 in 5. Okay. Do you see that, Wellington? Not 1 in 6, it's 1 in 5. Okay, because basically you're taking, the question is, I'm going to buy a blue fish. There's all these 4 types of fishes in the tank. So the odds of me getting, or the odds, or the probability of me drawing a blue fish is I take the number of blue fish, which is 6, divided by the total. In this case, it's 30. So 6 over 30, you want to reduce the fraction, is 1 over 5. And in terms of percentage, is 20%, because probability is usually notated by a percentage rather than 1 in 5. Okay? So does everybody understand that? Does anybody not see that? I'd rather ask that. Anybody not see that? Okay.
To calculate this probability, Sam needs to find out the total number of fish in his aquarium. Sam needs to add the 5 redfish, the 6 bluefish, plus 14 whitefish, plus 5 greenfish, to equal 30 total fish. Sam must also know the number of favorable outcomes. In his tank, there are only 6 bluefish, so his number of favorable outcomes is 6. The formula to calculate the probability is the number of favorable outcomes over the number of total outcomes. The number of favorable outcomes is 6, and the number of total outcomes is 30. So the probability of Sam scooping a blue fish the first time is 6 out of 30. Remember, all fractions must be in simplest form. So 6 over 30 will reduce to 1 over 5. The probability that Sam will scoop out a blue fish on his first try is 1/5. Compound events are a bit more complex than the simple events in the last example. Compound events involve the probability of more than one event happening together.
Okay, I'm going to start there because we're going to go on to that later on, so I don't want you to get confused by anything there. So we're going to go back to the PowerPoint. Okay. So let me just, so we talked about the event. I'm just going to make this a little, if I can make it a little larger. Okay, so as the lady in the video pointed out, you can have a line that goes from 0 to 1, or it's 0% to 100%. And just along the line, probability that our sun will disappear this year, that's 0. A 20% a chance a slowpoke will win the Kentucky Derby. At 0.5 or 50% the chance of a head in a single toss coin, as was pointed out in the video, because there is only 2 outcomes. At 70%, there's a chance of an increase in federal taxes, maybe. And at 100%, there's a chance of rain in Florida this year. I just want to point that out because it's rather important. When you talk about probabilities, you have to put it in the context of a time condition, okay? So the chance of rain in Florida this year, yeah, that's 100%. I don't believe that it has never rained in Florida. So you can say that. It doesn't really mean very much, but you can say that. So here's an example. The experiment rolling a die, or counting the number of members of the board of directors for Fortune 500 companies who are over 60 years of age. The possible outcomes of rolling a die, there's 6 possible outcomes. That's your total. in the example with counting the number of members of the board of directors, you have none over 60, one is over 62, 20, 48, or all of them are over 60. And some possible events, you can observe an even number, you can observe a number that's greater than 4, you can observe a number that's 3 or less, or whatever combination you want. And for the counting the number of members, more than 13 are over 60, fewer than 20 are over, whatever conditions you are setting up. So, does anybody have any questions about that? It's pretty straightforward about probability. That's simple probability. Okay. Okay. Oh, sorry. Okay. An independent event. This is an event that can be events can be independent, meaning each event is not affected by any other event. Okay. So this is very important. A coin does not know that it came up heads before, and each toss of the coin is a perfect isolated thing. Okay, even though the probability of getting a head and then a tail is 50%, or getting a tail and then a head. Okay, and they are different events. A head before the tail is a different event. A tail before the head is a different event. Where people get turned off by probability is you have to think about all the conditions that exist. So the example, you toss a coin 3 times and it comes up heads each time. What is the chance that the next toss will also be a head? It's still 50%, just like any other toss of the coin. They're independent events. Does everybody understand that concept of independence? Does anybody not understand the concept of independence? Everybody get that? Because when you toss a coin, it doesn't matter what you tossed 10 times before, 20 times before. It's still an independent event. But some people think it's overdue for a tail. But really, truly, the next toss of the coin is totally independent of any previous tosses. Saying a tail is due or just one more go, your luck is due, is called gambler's fallacy. You don't have to memorize that. But it's like, I don't know if people watched a movie or TV and somebody's sitting at a slot machine. That's where you put the money in the machine and you pull down a lever and it has to come up with 3 of the same icons. And, you know, some people, I've never seen it, I've never done it, I've never gambled. They may waste, you know, who knows how much money, a few $100s, thinking, well, eventually it will come up. Yeah, eventually it'll come up, but it's not necessarily based on any number because they're independent events. Okay? So, a dependent event, it means that they can be affected by the previous events. For example, drawing 2 cards from a deck. After taking 1 card from the deck, there are less cards available, so the probabilities change. Remember, there's 52 cards in a deck. You take 1 out, there's now 51, so the chances of drawing something previously, the drawing was 1 out of 52, now it's 1 out of 51. Okay? Everybody understand that? You are now reducing the sample size. So for the first card, the chance of drawing a king is 4 out of 52 because there are 4 different kings. There's 4 different suits. But for the second card, if the first card was a king, then the second card is less likely to be a king, as only 3 out of 51 cards are kings. If the first card was not a king, then the second card is slightly more likely to be a king, as 4 out of 51 cards left are kings. This is because you are removing cards from the deck. And the concept of replacement is when you put each card back after drawing it, the chances don't change as the events are independent. And without replacement, the chances will change and the events are dependent. So you draw a card out of the 52 and then you put it back into the deck. It's going to be the same percentage, same probability of drawing it the first time. If you don't replace, then you're reducing the deck by 1 each time, and the chances will change. So, any questions about that? Everybody understand that? All right. I'm just going to get to the video about independent events. Sorry, I got to change it here.
Independent events are events that do not affect the outcome of subsequent events. In an independent event, each situation is separate from previous events. An example of independent events would be the probability that it will rain on Monday and the probability of getting an A on my next test. These two events are independent of each other. The chances that it will rain on Monday does not affect the score on the next test. To calculate the probability of multiple independent events, find the probability of each event happening separately and multiply them together. Occasionally, when calculating independent events, it is only important that the event occurs at least once. This is referred to as the at least one rule. To calculate the probability of an event occurring at least once, it will be the complement of the event never occurring. This means that the probability of the event never occurring and the probability of the event occurring at least once will equal 1 or a 100% chance. For example, the probability of winning the grand prize in a local drawing is 1 out of 30. Tim and his wife Jane both bought tickets. What is the probability that at least one of them will win the grand prize? We first need to find the probability of Tim and Jane not winning the grand prize. Since the probability of one person winning the prize is 1 out of 30, the probability of one person not winning the grand prize is 29 out of 30, or 0.96. Remember, to calculate the probability of multiple independent events, in this case both of them not winning the grand prize, we find the probability of each event happening separately and multiply them together. Since both Tim and Jane have this.
Okay, sorry about that. Okay.
To a table, and on that table there is an empty bag. And the guy who runs the table says, look, I've got some marbles here, 3 green marbles, 2 orange marbles, and I'm going to stick them in the bag. And he literally sticks them into the empty bag to show you that it's truly 3 green marbles, and 2 orange marbles. 2 orange marbles. And he says the game that I want you to play, or that if you choose to play, is you're going to look away, stick your hand in this bag. The bag is not transparent. Feel around the marbles. All the marbles feel exactly the same. And if you're able to pick 2 green marbles, if you're able to 1 marble out of the bag, it's green, you put it down on the table, then put your hand back in the bag and take another marble, and if that one is also green, then you're going to win the prize. You're going to win the prize of, you're going to win $1 if you get 2 greens. If you get 2 greens, you're going to win $1. We say, well, this sounds like an interesting game. How much does it cost to play? And the guy tells you it is 35 cents. 35 cents to play. So obviously, fairly low stakes casino. So my question to you is, would you want to play this game? And don't put, the fun factor into it. Just economically, does it make sense for you to actually play this game?
Okay. So let me just ask you, is it worth playing the game to win is it worth playing the game and 35 cents to pay? What's the probability of you winning this game to get 2 green marbles consecutively? First of all, what's the probability of getting a green marble the first time you pull it out? It's 1 in 5, so what's that probability? 1 in 5? What's 1 over 5 equal? 20%, right? Okay, so you took a green one out the first time. Now you're asked to pull out another green. It's 2 out of 4. So what's the percent there? 50%, right, John? Okay, right, Brenda. So you know that to pull a green the first time is 20%, to pull a green the next time is 50%. So would people play this game? Is the probability that you're going to win better if you have to pull 2 consecutive green marbles out? Anybody? No? Why, John? Why did you say no? Does anybody say yes? Because 50% may not be enough to win. And you say that because why? What is that similar to? What's the 50% similar to? Flipping a coin, right? Because it's 50% you're going to get heads and 50% you're going to get tails. So if you think that 50% is not very high on the second one, then you may not want to spend the 35 cents. Okay, so let's see.
Let's think through the probabilities. So first of all, what's the probability that the first marble you pick is green? What's the probability that first marble is green? Actually, let me just write first green. Probability first green. First green. Well, the total possible outcomes, there's 5 marbles here, all equally likely. So there's 5 possible outcomes. 3 of them satisfy your event that the first is green. So there's a 3/5 probability that the first is green. So you have a 3/5 chance, 3 probability, I should say, that after that first pick, you're kind of still in the game. Now, what's the problem that what we really care?
Sorry, I was incorrect. I took 1 out. I was thinking of something else. So it'd be 3 out of 5. That's 60%. The second one is going to be 50%.
About is your probability of winning the game. You want the first to be green and the second green. Well, let's think about this a little bit. What is the probability that the first is green? First, I'll just write G for green, and the second is green.
Okay, if you've never seen this symbol before, looks like an upside down U or an N. That is a symbolic logic, and it stands for AND. So if this condition and this condition occur, then you get this kind of result.
Now, you might be tempted to say, oh, well, maybe the second being green is the same probability. It's 3/5. I can just multiply 3/5 times 3/5, and I'll get 9/25. Seems like a pretty straightforward thing. But the realization here is what you do with that first green marble. You don't take that first green marble out, look at it, and put it back in the bag. So when you take that second pick, the number of green marbles that are in the bag depends on what you got on the first pick. Remember, we take the marble out. If it's a green marble, whatever marble it is, whatever after the first pick, we leave it on the table. We are not replacing it. So there's not any replacement here. So these are not independent events. Let me make this clear. Not independent. Not in particular, the second pick.
So very important, because this is about dependent events. When you see this symbol that looks like an N, it means the first event has to occur, and the second event has to occur, and then you figure out that probability. It's not if the first event occurs or the second event occurs. That is a different probability. So these are dependent. The second one is dependent on the first.
Second pick is dependent on the first. Dependent on the first pick. If the first pick is green, then you don't have 3 green marbles in a bag of 5. If the first pick is green, you now have 2 green marbles in a bag of 4. So the way that we would refer to this, the probability of both of these happening, yes, it's definitely equal to the probability of the first green, or the probability of the first green, times, now this is kind of the new idea, the probability of the second green, given this little line right over here, just this straight up vertical line just means given. This means given that the first was green. Now, what is the probability that the second marble is green given that the first marble was green? Well, we drew the scenario right over here. If the first marble is green, there are 4 possible outcomes, not 5 anymore, and 2 of them satisfy your criteria. So 2 of them satisfy your criteria. So the probability of the first marble being green and the second marble being green is going to be the probability that your first is green, so it's going to be 3/5, times the probability that the second is green given that the first was green. Now you have 1 less marble in the bag, and we're assuming that the first pick was green, so you only have 2 green marbles left. And so what does this give us for our total probability? Let's see, 3/5 times 2/4. Well, 2/4 is the same thing as 1/2. This is going to be equal to 3/5 times 1/2, which is equal to 3/10, or we could write that 0.30, or we could say there's a 30% chance of picking 2 green marbles when we are not replacing. So given that, let me ask you the question again. Would you want to play this game? Well, if you played this game many times, on average, you have a 30% chance of winning $1. And we haven't covered this yet, but so your expected value is really going to be 30% times $1. This gives you a little bit of a preview, which is going to be 30 cents. 30 cents, 30% chance of winning $1. You would expect, on average, if you play this many times, that playing the game is going to give you 30 cents. Now, would you want to give someone 35 cents to get on average 30 cents? No, you would not want to play this game. Now, one thing I will let you think about is, would you want to play this game if you could replace the green marble, the first pick, after the first pick? If you could replace the green marble, would you want to play the game in that scenario? Let's imagine ourselves in some...
Okay, sorry about that. So his last question, if you picked a green marble and then you put it back in again, what would the probability change to? So now you have 3/5 times 3/5. And what do you have there? you're going to increase your probability, correct? Because you're going to have the same probability of picking it, the green one, the second time, because now the same amount of total is there. So the first time it was 60%, the second time it's going to be 60%. So the probability then becomes 60%. It's better than 50, but it's up to you. But there's a better chance of you winning the 35 cents more often than you're losing it. Okay, any questions about that? No? It's relatively easy, straightforward. So you already know that when there's probability with no replacement, the percentage is going to go down if you keep figuring out probabilities. The probability is going to stay the same if you do replacement, and that is a very important concept. All right, so we'll stop there, and for those that are really anxious, the test will be available like in 9 minutes. Anyways, have a good weekend. And for those of you interested, then we have the office hours on Monday, okay? So take care and have a good weekend, everybody.